So our galaxy is the Milky Way. It's the name of it. Via Lacta in Latin, Milky Way. And we can see it when we look out in the sky at night. We see the faint band of light arcing across the sky, little darker pieces in it now and then from the dust. The bright part has gas in it. It's got stars and nebulae, and you can some parts of it you can see it reddish and bluish of nebula colors. And so we know a little bit about our galaxy. It's got dust and gas and so forth in it, but from the inside, it just looks like a streak across the sky, a band across the sky. And so the question is, what kind of galaxy is it? Could this be like an E7 or a real flattened sort of elliptical galaxy or a spiral galaxy? Well, Jan Oort, who's most famous for figuring out about the Oort cloud of comets, teamed up with Walter Baade to try to map the galaxy. Now, Oort's more famous for comets, but he really kind of thought his work on mapping the galaxy was really some of his more important work. Baade, of course, we already have seen him multiple times here doing all kinds of important things. So they came with an idea for trying to figure out the type of galaxy that we're in. First of all, they figured out that it's got to be a type of spiral galaxy. That's because it's got dust and gas in it. So we want to figure out what type of galaxy it is. So it's a spiral galaxy, so that would be barred spiral or non-barred spiral, SA, SB, SC, something like that. So how would you tell? You can't go outside the galaxy and look back and see what it looked like. So how would you be able to do that? Well, Baade and Oort got to thinking. We got this. Imagine we got right there. We've got the sun. And they said, well, we can sort of figure things out because we know that young stars form in regions where there's a lot of dust and gas. That's along the spiral arms. So they started mapping out places where young stars were forming in the sky. I didn't really tell them a whole lot, just a bunch of stuff. And they said, well, we also have some high-mass supergiant stars. And the high-mass supergiant stars, come from stars that don't live very long, and so we can start mapping some of those. And then we got some young star clusters, so we can map where some of the young star clusters are. And then we can start looking at a few other things, some neutron stars, pulsars. Okay, we can look at a few other sort of things. Again, dark nebulae, regions where you're getting the process of starting star formation. And they started doing that, and they realized once you start doing a whole bunch of these things, you start noticing kind of a pattern developing here of spiral arms going by. So we're on the edge of a spiral arm right here. And so, again, we know the space is not empty between the spiral arms, but these are the places where from far away it would look bright as the spiral arms and dark in between. And so by looking at the wrapping of the spiral arms, they realized it's fairly well wrapped and pretty distinct. So that means we definitely are not an SA. So they started thinking we're either an SB or an SC. So that was their thinking. There was no evidence of a bar in the initial observations. So that was their first thought. So this was the very first attempt. So fairly tightly wrapped spiral arms, and we named them. The star in Orion happened to be our spiral arm, so we call that the Orion arm. Next arm out is the Pegasus arm. Next arm closer in is the Sagittarius arm, because this is the direction of Sagittarius. Now, galaxies look like big spinning things. So the question is, are they really spinning? So how would you actually measure the rotation of a galaxy? You could sit and look at it. You could watch it for a few 100 million years and see if they rotate. Well, that's not realistic. So we say, how else could we do that? Doppler shift. We could look at one side of a galaxy, another side of the galaxy, and see, are they Doppler shifted? In fact, we find that they are. So that does indicate that they are rotating. In our own galaxy, we can find the rotation of our galaxy. So if we imagine the galaxies rotating like that, the stars that are in closer are going to go faster than the ones further away. So that means these stars are coming towards us. That's blue shifted. These are going away. That's red shifted. We're going faster than these stars, so they're red shifted. Those are blue shifted because we're getting closer to them. And so Jan Oort works this out, and sure enough, we find that most of the stars, the Milky Way, can be divided into these quadrants that are blue shifted or red shifted. And so that does indicate that, in fact, the sun goes around the galaxy, and the galaxy is, in fact, it's differential rotation. And so that means that the stars that are closer rotate faster than the ones that are farther out. A galactic year is the term that we use to describe how long it takes to go around. The whole different parts of the galaxy have different amount of time. So the term galactic year usually means how long does it take the sun to go around. And it's about 225 million years. The sun's moving about 220 kilometers per second. And stars that are in closer take less time to go around. Stars that are further out take longer to go around. So stars in close, less time. Stars further out, longer time. And so from that, we can measure rotation rates of galaxies. We can also measure galaxies using radio telescopes. Remember, we talked about how hydrogen, neutral hydrogen, the electrons can be in one orientation or another orientation. So it can be one orientation or the other orientation. This orientation here has less energy. So if it starts in high energy, goes to less energy, then what's going to happen is it's going to give off light. And that light goes off at a wavelength of 21 centimeters. So we can measure that. Now, if we imagine we're looking at a galaxy here, then part of it's going away from us, part's going away from us faster here. So how far away it is along our line of sight, the direction of motion is going to be changing the amount of Doppler shift. So if we look at our own galaxy with radio waves, which looks through our medium, so it looks through all the interstellar medium, then we can measure, by measuring the Doppler shift, how far away blobs of gas are. And this gives us a measure here. Now, if we look straight across this way, then we don't see very much because everything's moving off to the sides. It all has the same Doppler effect. This is a very tightly wrapped galaxy right here. There's another image right here. Again, a very tightly wrapped galaxy, also using these different radio waves and Doppler shift. And so it's a very tightly wrapped galaxy. That's suggesting rather than an SB, we're actually a little bit closer to maybe even to an SC. A lot of tightly wrapped spiral. We know that the radio waves are a good way of doing it because we already talked about this before. The galaxy M83 in visual light, we have this, and then in radio wave we see that. And again, the radio waves tend to line up in places where it looks otherwise dark. Where it looks bright in the visual image, it's dark in the radio waves. That's because the radio waves measure neutral hydrogen, whereas the bright lines, the bright parts of the spiral arm are the ionized gas, the glowing and energetic. And again, it's energetic, so it's warmer, so the infrared view very closely matches the visual view. We can also measure how much interstellar medium is in different directions close to us, and what we discover is that close to where the sun is, the interstellar medium is actually a lot thinner and hotter than it is in most of the galaxy. It's almost like there's a big bubble in the interstellar medium of hot, thin gas. Well, in fact, we call that the local bubble. And so the sun is located in this local bubble. Now we're not always in the local bubble. It turns out that the local bubble is there and the sun's moving through the interstellar medium. So right now we happen to be in this. There's actually a little patch of thicker interstellar medium here very close to the sun, that's slightly not as thick as it is in normal intergalactic space, but a little bit thicker than the rest of the local bubble, and we call that the local fluff. So these are some of the stars in our vicinity and how they relate to the local bubble. Local bubble also appears in infrared light, so which looks at the interstellar dust. Local bubble probably is due to a supernova in the distant past. It's probably only 10 or 20 million years old, about 300 light years across. Sun's moving through it, and probably it's only been in the local bubble for 5 to 10 million years. So the supernova was not very close to us. We were actually moving towards where the supernova was. And so we've been in this local bubble for 5 to 10 million years. The local bubble itself is probably between 10 and 20 million years old, and due to a supernova. The local fluff, sun's only been in the region of the local fluff for a few tens of thousands of years. In another 10 or 20,000 years, it will exit the local fluff. The local fluff is a little bit denser than the local bubble, but it is a little bit thicker than or rather, a little bit less dense than the rest of the interstellar medium of the Milky Way. Now, the question is, when we're passing the local bubble or the local fluff compared to the rest of the interstellar space, how does that affect the solar system? Well, where the gas is thinner, the sun's magnetosphere, or magnetodomain, actually pushes further out. And so that means interstellar space is further out. So right now, they originally had estimated that the Voyagers would have reached interstellar space long before they did, because they didn't realize that we were actually in a bubble. And so that makes it a little bit more, the sun's magneto influence goes out further. Well, that actually has an impact on Earth too, because it also impacts cosmic rays. And so that does beg interesting questions, because it does mean that possibly the cosmic rays could relate to mutations and evolution. So whether the sun is in a bubble or a fluff or whatever does impact us a little bit. The central region of the Milky Way, we now know, has a bar in it. The bar was very difficult to detect visually. It's impossible to detect in radio waves. It was difficult to detect until modern technology. So only in the last 15, 20 years have we really realized there's a bar in there. Bar's about 45 degrees with respect to our line of sight, which actually makes it even tougher to detect. But it does bring out a couple of things. They used to think there was a region here of like a miniature spiral arm that was expanding outwards, and it turns out that's just really the edge of that bar. So this is what's going on in the core of the galaxy. So our galaxy right here, dwarf galaxies orbiting around. We got a bar in there. This is kind of a sort of schematic of it. Edge view of the galaxy looks something like this up at the top. So it's a bar. We're somewhere between an SBB and an SBC. And again, they used to think it was an SB or an SC, and we now know there's a bar in there. So we sometimes write that as an SBB/C to indicate what we think our galaxy is. So this is how we actually map the galaxy. I just thought this is cool. In Hawaii, there's an astronomy center that has a garden that's planted in the shape of the Milky Way. So I just thought that's kind of a very cool sort of thing.